Okay, hello everyone. And this video, I'm going to show you another example of statically indeterminate problem in torsional loading. Okay, and here is a coaxial member. It's a coaxial member, and it's a coaxial member. The shell is made of steel. Okay, this is steel, okay, made of steel, and the core is made by it's called brass. 中文 means 黄铜 okay, this is a coaxial member. And it says the coaxial member it's fixed on this support. Okay, it's fixed on this support. And it said if we apply a torsion, if we apply a torque, if we apply a torque at this end 8, okay, and this torque is 250 Newton times meter, okay, and he say what's the take if torque applied plot the shear stress distribution along radial line of its cross-sectional area. Okay, so this problem he wants to, okay, if we apply the load here, apply load at the end, okay, and then calculate the radial distribution of the shear stress distribution. Okay, so how to solve this problem? Okay, so this coaxial problem. This is a coaxial when we apply the external torque on this material, okay, on this coaxial member, and at the same time the steel and brass also will generate some torque, okay, when we apply the material. I'm not sure for sure. Okay, so let's use the cut section method. Okay, if we cut a section here, okay, if we cut a section here, okay, cut section here, so here is our coaxial loading, okay, and we cut section here, okay, here is A, okay, and then we say you apply external torque, okay, apply external torque, okay, the external torque is counterclockwise, T is equal to 250 millimeter Newton times M. Okay, so, and when you cut section here, so here we have the, how to say that, okay, we say this is between A and B, let's say there must be a torque here, torque TAB here. And because overall is static, overall thing is static, so T plus TAB must be equal to 0. Okay, we assume it's all counterclockwise, so it's all positive. Okay, so we already know that TAB is equal to minus 250 and Newton times per meter. Okay, so when we apply the torque here, apply external torque, then the internal of the material have another torque to make the whole system static. And this torque must be aware. This torque, because we have made this member is made of two material. Okay, so each component will contribute to the torque. Okay, because this coaxial member, they attach to each other. So they all must be contribute the total torque of the system. So okay, so TAB, and then so we have the TAB is equal to like a torque. Let's say one is steel, the other is brass. Okay, so steel plus brass. Okay. Okay, I hope you can understand this point. Okay, the internal torque is contributed by the each material. Okay, not only by the steel or only by the brass. Actually, the two material all share the share to this TAB. Okay, and okay, so we know the TAB is equal to minus 250. So TS plus TBR is equal to minus 250. Okay, so the problem wants us to calculate shear stress distribution. So that means shear stress distribution. That means we need to calculate the shear stress. Okay, so in the torsional member, how to calculate shear stress? Do you remember now how to calculate shear stress in the axial in the torsional twist? Okay. I remember the shear stress tau. I need to check. Show the shear stress. Okay, shear stress is T. Yeah, I forgot. Shear stress is equal to TC over J. Okay, shear stress is equal to TC over J. Okay, T is a torque, J is a polar moment of inertia, C is a radius, right? So if we want to know the shear stress, we want to know the shear stress distribution. So we need to know the radius. Okay, and polar moment of area, we know it because this already gives us motivation. The inner radius, the inner diameter is radius. It's diameter or radius? Oh, it's radius. Okay, it's radius. R inner is equal to 10 millimeter, and R outer is 20 millimeter. It's give you the radius. Okay, so it give a radius. So it give a radius, and so we know the radius and the polar moment of inertia. And so if we want to know the stress, all we need to know is find the torque. Okay. But right now, we only have this equation, TST plus TBR equal to minus 250. So, okay, that's if we use the rigid body equilibrium balance, we get this equation. But we only have one equation. We have two unknown. So, right now we cannot solve T because we only have one equation. So we need to find another equation. Okay, so this is the so-called statically indeterminate. If you rigid body equilibrium, you still cannot solve the problem. So you need to find so-called competitivity equation. Okay, and in this problem, in the competitivity equation, what is the competitivity equation here? In this problem, the competitivity equation is the angle twist of the steel is equal to the angle twist of the brass. Okay, because this is a coaxial member. Okay, so if we apply a torque, these two members have the same. These two materials have the same angle twist because it's a coaxial, and these two materials attach to each other very firmly. So when you twist the material, this steel and the brass will have the same twist angle, but they contribute these two materials contribute differently to the total torque, but they share the same twist angle. Okay, so think about it by yourself. Okay, I think maybe sometimes it's hard to imagine that. Okay, so this is another equation we have. So this so-called competitivity equation in this problem. So what's the formula for the angle twist? Do you remember that angle twist is equal to, I think I need to check the notes. It's TL over JG. Okay, TL over TLL over GJ. Okay, so we use the competitivity equation. So we start with is so what is phi ST? So with TST we don't know, LST and the GST. And the JST is equal to the TBR, LBR, and GBR, JBR. Okay, and LST and LBR is the length. Okay, the length because it's coaxial problems, the length is the same, so we can cancel this out. No problem, cancel this out. Okay, and the other thing is lots of things we have to compute. Okay, first of all, what is the shear modulus of this or modulus of rigidity? Okay, but I believe it's called shear. Maybe shear modulus is more proper. Shear modulus, this is 80. ST is 80 gigapascal and GBR is 36 gigapascal. Okay, so let us write down this. Okay, TST we don't know. Okay, so 80 gigapascal. 80 gigapascal and the time JST equal to TBR, and here's BR is 36 times 10 to the power 9 gigapascal and times JBR. So what's the polar moment of ST still in the JBR? Okay, so be careful. Okay, so let's calculate what is JST. JST, because JST is not a complete circle. It's hollow. Okay, it's hollow. Still is hollow. Okay, so it's equal to 32 over pi DO4 minus DI4. Okay, be careful, it's diameter. Okay, and then for the JBR, it's a complete circle. It's a complete circle, and there's no hole on the BR. No hole on the BR, and it still has a hole. So it's just equal to pi over 2 and the D4. Okay, so let's put everything in there. Okay, so D out is, okay, because it gives you the radius, but I prefer use the diameter, so you have times 2, so it's 40. So it's 40 times 10 to the power minus 3 power 4 minus 20 times 10 to the power 3 4. Okay, so I think needs some calculation. Yeah, that's it. It really needs some calculation. Inner is 20 times 10 minus 3 4. Okay. Okay, let's see what's the number. It. Let me check. Yeah, it's really okay for the steel. If you do the calculation correct, I think the value is 2.355. It's 2.355 and times 10 to the power minus 7. Okay, that's the first one, JST. Okay, let me check. Okay, and the other is the JBR. JBR, if you calculate right, the value is what would be 1.57 times power 10 to the power minus 8. Okay, so if you have JST and JBR, you can put a JST and JBR in this equation. Okay, looks like I don't have any space here, so okay, so where should we put it? Okay, maybe I put this here. Okay, JST and JBR, so it's 2.355 times 10 to the power 7. Okay, so that's okay, so that's JST. So maybe I write small, 2.355 times 10 to the power minus 7. So what is JBR? JBR is here. So JBR is times 1.57 10 to the power minus 8. Okay. Okay, so and finally you will have this. Sorry. So finally you have this TST equal to TBR, and here is 80. It says 10 to the power 9. So 9, 10 to the power minus 7. So here is 100. So 100. So 100 times 80 times 2.355 is equal 18840. And the other is 10 times 36 times 1.57, so it's 565.2. 565.2. Okay, so we will have the TST steel tension is equal to how much is this? And let me see, times 18840. So it's equal to 33.333. Okay, looks like 100除以3 looks like 3 over 100 looks like. Okay, so sorry, TBR times TBR. Sorry. TST is equal to TST is equal to 33.333 TBR. TBR is 100/3. Okay. So so we have this relation TST equal blah 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 TBR, and we have TST plus TBR is equal to minus 250. So can we solve the TST and TBR? Of course, we can solve TST and TBR. So okay, let me erase this equation. Oh, sorry. So I have to erase this part. So okay, let me erase this part. So we are going to get the final answer. So you have relationship between the TST and TBR. You have two unknown. Right now you have two equations. So I think you can solve the TST and TBR very, very easy. Very, very easy. Okay. Okay, so you have these two equations. Okay, and this one and this one. Okay, and combined together. I think you really just try yourself. Try yourself. Just try yourself. Just try yourself. So I think you will have the TBR. You will have the TBR is equal to my answer is 7.282, and it's Newton times meter. And the TBST is it's minus. Why I'm doing the minus TST plus TBR. Do I have the minus? Oh, I think I should have the minus answer. Let me see. Do I have minus answer? TST is still plus TBR plus TB. Plus BR. Is this equation wrong? Let me check. I think the equation, I think it's right. Okay, till now is already the problem is this minus sign. Let me check. Do I really this T plus TAB? Then problem. Yeah, TAB is equal to this, and the yeah, I think it's minus sign here, and here is a minus. Yeah, 242.718 Newton meter. Okay, so I still assume because it's towards my negative sign, so actually it should be clockwise. Yeah, that means it's just clockwise. Okay, that just means it's clockwise. So if it's clockwise, okay, that's no problem. Just direction issue. The magnitude is the same. Okay, so the next thing is, okay, if we know the torque for each material. Okay, so we can calculate the torque. We can calculate the shear stress. Okay, so for the shear stress, let's calculate shear stress from the steel. Okay, shear stress steel, and we can calculate the maximum. Maximum is on the outermost radius. Okay, shear steel, and the maximum is TC over J. I erased the J. Yeah, I erased the J. Okay. So here, we temporarily forgot the minus sign, because minus sign just means the direction. So we just here we just put the torque in this formula, and okay, the outermost is the maximum. Outermost, the C is a radius 20 times 10 to the power minus 3. Okay. And the denominator is J steel. Okay, J steel. Yeah, just erase this. J steel is okay. I just erase it, but I think I have the notes here. J steel is 2.355 10 to the power minus 7. So it's 2.355 times 10 to the power minus 7. So the maximum is, okay, let's see. Okay. Oh, it's very small. Okay, 242.718 times 20 divided 2.355. And so this will be 10 to the 7, 4, and 2, 6. So it's 20.61 megapar. Okay, it's megapar. My answer right? This is steel. Okay, so the first one is right. And the steel mean is at the inner radius, and we already, because in previous section we talk about, in this class we assume the shear stress distribution is linear. Okay, it's linear, and it's linear dependent to the radius. So the outermost is 20.61 megapar. And we want to calculate the inner radius shear stress. We just divide it by, it's 20 over 10, 10 over 20. So yeah, it's very easy. It's about 10 to the 0.31 megapar. Okay, and okay, so that's for steel. And the max of the brass, okay, the max for the brass, okay, because the max of the max shear stress on the brass, the same thing is the maximum is on the outermost radius of the brass. So outermost radius of brass. So okay, the brass and the maximum, I believe it's all equal to TC over J. So T is 7.282. Because right now we just ignore the negative sign, because negative sign just means the direction of the torque. So, and right now we don't need to consider the direction, we only consider magnitude. So, and so TC over the C is 10 times 10 to the power minus 3. And J brass, okay, I think previously we calculated J brass is 1.57 times 10 to the power minus 8. So it's 1.57 times 10 to the power minus 8. Okay, so let's do a calculator. 7.282 times 10 divided 1.57. And times 10 to the power 5 divided 10 to the power 6. So it's about 4.64 megapar. Okay. So the maximum shear stress in brass is about 4.6 megapar. And you see the minimum stress and the maximum stress on the steel is at least 10, because 10 between 10 to 20. So from this shear stress distribution, you will see that the steel takes more stress. Okay, in the coaxial member. If you have a stiff material, okay, stiff material, how to judge, how to determine it's the stiff material or not, just based on, just determined by the modulus, and this problem is shear modulus. So the shear modulus of steel is 80 gigapar. The shear modulus of brass is only 36 gigapar. So yeah, in terms of shear, so steel is much harder than brass. A harder material will take a lot of stress. Okay, that's good, because that means this steel can protect steel that can protect the brass. Okay, because when you apply the external torque, the steel will take more stress than the brass. Okay, so the steel can protect the brass. Okay, I think that's a meaning of the coaxial, the coaxial material or coaxial member. Okay, the outer shear have large radius and larger elastic modulus or shear modulus, and protect the material inside, protect the core material. Okay, and here, yeah, this is a very very general example for a statistically indeterminate problem in torsional member. Okay, yeah, remember like we have similar problem in the axial loading, right? Okay, well, in axial loading, we also have coaxial problem. It's also statically indeterminate, and the conclusion the same. That the stiff material will take more stress. It take more external stress. Okay, share more external stress. Okay, and protect the material of core material. Okay, so here's the example. So I think, yeah, in this problem, I didn't draw the shear stress distribution. I didn't draw it. I didn't, because the problem is they want to plot. But next slide, I have the plot, so you can read by yourself. Okay, here you draw a plot, and you can read by yourself. Okay, it's just basic what I just said. Okay. Okay, okay, so I just start video here. Okay, see you in the next video. Okay, see you next time. Bye bye.